they cling to the dot matrix stuff because it's too expensive to upgrade everything, you know? So, everything is a macro version of that.
All right, so again, make sure you turn in your homework if you have it. And let's go over some of this. So how was the homework? Any major issues?
Describing that one sentence was fun.
Yeah, first I was thinking, find a way to describe it in simple, one line.
I took 2 lines and called it
Yeah, I did say.
Yeah.
I was wondering if we could just do some more of the recurrence relation stuff, like an example of that.
Oh yeah, definitely.
The recurrence relation question in this homework was a little bit tricky because setting 2 different recurrence relations for the even numbers and the odd numbers in the set. Either we might have covered that, we might not have. I checked the lectures, I didn't see anything directly pertaining to it, but I remember that my calc reading.
All right, let's look at recurrence relations. So, we can write an expression for a sub n, right? If we consider this to be 0, 1, 2, 3, 4, 5.
Should we start at 0?
We could. We would make it a little harder and start at 1, but I'm going to be lazy. If we were to start at 0, a sub n would just be 2 to the n. And we know that because we understand powers of 2.
So, what if we made a set that does something like S2n is equal to something like that, and then S2n plus 1 is equal to something like that, okay?
Yes. This is not, I mean, this is true, but it's not really a recurrence relation. This is kind of a solution to the sequence. If we actually want a recurrence relation, we're trying to define the nth term in terms of the earlier terms. And we might say something like a sub n equals 2 times a sub n minus 1, and a sub 0 equals 1 in initial condition. And that's more the feeling of a recurrence relation. We've defined how to find this in terms of other terms in the sequence.
So that the actual solution you would be looking for is the an function and the initiation terms?
Yeah, usually you have a relationship and you also have some initial condition, but there may be cases where you don't need the initial. I can't think of one. But so this is how to think of that sequence as a recurrence relation. What about this? See again? How about as a recurrence relation? Yes, it's negative 2 to the n.
Wait, what? Oh, right, yes.
Well, how would you describe the nth term in terms of earlier terms in the sequence?
Multiplied by -2.
Yeah, it's still just a negative 2. So how about well, I'm just going up by 1s here, so I switched it up on you. It's not powers of 2 anymore.
Well, it's...
You might be able to use a trig function.
Yeah, you might actually.
I would just say change the parameters if a to the n or AN is odd versus AN is even.
Okay, so let's start from 0. Let's start it that way. So AN equals, and if AN is odd,
It just equals AN.
it's just AN minus 1.
Oh, yeah.
If n is odd. If n is even, how can we describe an?
Is
AN
AN minus 2?
1 plus an minus 1.
Yeah, we do it that way.
And then initial conditions. I think that's, do we need another initial condition? Right, because that'll define A1 is the same as A0, and then A2 will be 1 plus A1. Yes, that'll get us started.
Can we just say n greater than 1? Greater or equal to 1?
Yes, but
Instead of
we
It's not
still
2
need,
equal to 1.
we still need to define what the previous terms are so we get a reasonable value in the A to the N equation.
Yeah, we need a way to sort of seed the whole operation.
But if we determine what's n, then a, like,
So what are you suggesting here?
I'm saying instead of writing that n greater than or equal to 0.
So,
Yes,
And
so then
what goes over here?
n0 is equal to n minus 1. Or like in a different terms, but don't write in a0.
do you want to put it on the board?
Like in different term for these, but
And greater than or equal to 0, then it's going to be A0 is equal to A0 minus 1. Right, we don't write this anymore. We just determine what is
n the starting point of n.
Mhm. Right, but so how do you know what A0 is?
Then we are going to, actually I wrote something on my paper, I don't remember how they.
Okay.
Can I have my paper from those?
Yeah.
We should do this.
Yeah.
So like this one. Or the other.
Whatever the term was, like here was
Mhm.
1/2 minus 2,
Mhm.
and like for A2j is equal to 4 times k minus 1. Then we are going to say like k is greater than or equal to 1 or 0.
Okay.
Then we don't have the starting point.
Yeah.
A n.
If you don't have the starting point though, how do you know what say A2 is equal to?
N always starts from 1 if we don't say when it starts from.
Okay.
Or we can say n starts from like 2, 0.
So what would A1 be equal to?
A1 is going to be equal to k equal to 1, so if it's 1, A1 is going to be 1/2 2a minus 2, which is going to give us,
So it looks like it would be 1/2 A0.
yes,
So what is A0 equal to?
A0 is the first term that we get from
But
here.
how do we know that?
It's the first term.
Well, what's its value?
The value is the value of the first element.
But you don't have that, all you have is this.
No, I'm saying how we, the way that we get this from this formula.
Mm-hmm. So if all you have is this formula, and I say, what's the value of A0, there's nothing here that tells you that. And all right, cool, thanks. I'm going down this path because this is a critical point to what we're doing in about another week or two. So look at this, right, where we just had, well, let's look at an even simpler one. Let's just look at a succession of numbers. And I can say an equals 1 plus an minus 1, and a0 equals 1. If I don't have this, this relation also describes this sequence. So we've captured most of the essence of this sequence, but we're missing one point, which is where do I start? And this, if we just try to find what A1 is, it's going to be 1 plus A0. What's A0? The only thing we can say is it's 1 plus A minus 1. And A minus 1 doesn't exist, but it would be 1 plus A minus 2. And we're going to kind of descend forever down this path.
I had a question on the sequence you erased, the 1, 1, 2, 2.
Mm-hmm.
Could you have it as an equals a n minus 2 plus 1?
Yes, I think that works.
Condition a0 equals 1 and a1 equals 1?
Yeah, I think that works too.
Okay.
And I think that's what I had in mind with this question, but we'll look at this question still in a minute.
I want to make sure that you can actually have two.
Yeah, you can have 2 or more initial conditions,
Okay.
definitely. This is something we're going to come back to and talk a lot about when we talk about mathematical induction. We're going to need 2 things. We're going to need an inductive step, which corresponds to this. Once we're at some point n, how can we get to a point further on? But we're also going to need a base case, which says where do we start this whole process? And we'll see some examples where without that base case, we can get into some weird contradictions. So that's what's going on there. Yeah?
I forgot my initial condition, like, is that completely wrong then?
Minus 29 billion points. Yeah. No. Yeah, that's a minor point, grade-wise, for this. So let's look at the weird sequence that I put on here. It's really hard to like write without any typos. So there's 2 doubling sequences here. It depends if you start from 0 or 1 or something else. But if you start from 0, the odd terms start from 4, 8, 16, 32. The even terms start from 1, 2, 4, 8, and so on and so forth. So one way to do this would be a sub n equals 2 times a sub n minus 2. Because each term is just twice the term that came 2 before it. But that does not work for a1 or a0. That only works for n bigger than or equal to 2. And then we can have some initial conditions. A1 equals 4, a0 equals 0. Sorry, 1. You can also do it with cases where n is even or odd. I think there's a way to do that. But does this make sense that this defines this sequence? So what about a sequence like this? Now we're back into those horrifying standardized test days. Find the next number. Would you recognize these?
That's pretty straightforward.
What is it?
That's clever.
Well, it's +2, +3, +4, +5, +6.
Yeah, so these are your triangle numbers. So 1 plus 2 plus 3 plus up to some integer n.
N minus 1 plus n.
an minus 1, yeah, an minus 1 plus n.
So something like that, depending on where we start numbering from. And I think we have to start numbering from
If we
1.
start at 0, yeah.
And we have to seed it. A1 is equal to 1. So then A2 is 1 plus 2 is 3. A3 is A2, which is 3, plus n is 3. Gives you 6, and so on. And if we're mathematical-ish, we might say something like an equals, and I always get this off by 1, n times n plus 1 over 2. That's also true. But without knowing that, we can define the sequence with this pair of equations, this recurrence relation, and initial condition. And the cool thing is we can code this. Right, we can write a C program that computes this function using this recurrence relation. You can say if you want to evaluate the value of this function at n, if n is 1, return 1. Otherwise, take n, evaluate the function for n minus 1, add those together, return that. That's a recursive function. And again, we'll do a lot of recursive programming in 222. And this is all we're doing. We're playing with these relationships. But we're also going to want to be able to prove that this gives us what we claim it gives us. We're going to be able to do that using mathematical induction. All right, so how did you interpret this set in question 9? So what's A cross B look like?
A cross B.
The Cartesian product of A and B.
Just
Oh, that
A cross B?
Yeah.
That's, that would be head 1, head, or sorry, head 1, head 2, head 3, head 4, head 5, head 6, tail 1, tail 2, tail
Cool.
3.
Great, so that's asking us to find what is equal, not like...
No, you're asking, it asks you to find the number of elements in there.
That's what A wants, and then B wants you to.
So it's head 1, head 2, 6, tail 1, to tail 6. So how many elements in A cross B?
12.
It's 12, and it turns out it's always going to be the number of elements here times the number of elements here, at least for finite sets. So it's 12, and if you wanted to actually list them, this is what it would look like, although I didn't ask you to list it. But then in B, I asked how could you interpret this? So who came up with an interpretation for this?
It's just the probabilities of what
It's-
results.
It's
all
it's
possible
all
outcomes.
possible combinations.
There we go.
Of,
You could use that to calculate the probability.
right, all combinations of,
Flipping a coin and rolling a die.
sure,
Yes.
flipping a coin, rolling a dice. Or choosing head or tail, or choosing the number 1 through 6, if you're very literal about it. But yeah, that's one way to think of it. Flip a coin, roll a die. You're going to get one of these 12 possibilities. Other homework questions? Or questions related to all of this stuff? Because I'll probably pop a quiz on you Friday on this stuff.
Yeah. You roll over cardinality again.
Yeah.
Yeah, so there was a lot of discussion on that on Canvas. For a finite set, cardinality is the number of elements in the set. For something bigger than a finite set, for an infinite set, it's a different way of measuring the size of the set. And we can't really give it a meaning beyond that, but we can work with cardinality in a few ways. We can say the cardinality of A equals the cardinality of B if there's a one-to-one correspondence. the elements of A and B. And remember, this is our existential qualifier. There exists.
I think you already answered my question last week, but I just forgot that. How could the cardinality of real numbers be equal to cardinality of real numbers between like 1 and 2?
Mm-hmm.
They're
Good
equal while one of those is covering the other one.
Really good question. How about the cardinality of all integers being the same as the cardinality of positive integers?
Yeah,
Is that a similar question?
it is.
Okay. How about the cardinality of positive integers and the cardinality of even positive integers?
Yes.
Similar question.
They're all
Similar
the-
question.
They're all the same. I'm still not, yeah, I'm agreeing though, I don't see how that works.
Because there is element that which is not included, but there is one-to-one correspondence.
All right, so here's our two sets. You got an answer?
I was just gonna say that Wikipedia had a nice picture to kind of explain it. But you're probably gonna draw the exact same thing for it.
Maybe.
Yeah.
My one-to-one correspondence is multiplication by 2. Any positive integer multiplied by 2, I get an even positive integer. Any even positive integer, I divide by 2. And I get a positive integer. So every element of here corresponds to exactly one element here. And every element here corresponds to exactly one element here. That's what a one-to-one correspondence is. So that's why we say that these two sets have the same cardinality. Not because they feel like they have the same number of elements, but because there's this one-to-one correspondence. Yeah?
Instead of using like this set of all even positive integers, like if you just changed like the 6 to like a 7, would it still have the same cardinality?
Sure.
Because there's still like a one-to-one mapping, but it's not like the same. Like, does it
Yeah.
matter if you can like, you know, find one from the other just by multiplying or dividing?
We
by the same
don't
number every time?
necessarily need to be able to find this function. And there's times when we can say two things have the same cardinality, but not actually be able to name an exact function.
Okay.
But I think any infinite subset of the integers will have the same cardinality.
Okay.
Because we can pick the smallest, let's just look at positives, we can pick the smallest integer in this other set, map that to 1, pick the next smallest integer, map that to 2, and so on, and that'll give us a good mapping.
So what about the cardinality of rational numbers?
Rational numbers are the same as integers, and that's from countability. So cardinality, aleph, not, we also call those sets countable. Because if we can order them, we can do this map, the first one to 1,
Yeah,
second to
that's
2,
right.
so we did that zigzag on the matrix of rational numbers. But real numbers have a bigger cardinality.
So if you were to say this cardinality of the set R not Z, where it's all the numbers in R that are not in Z,
Mhm.
is that still a larger cardinality?
That's the same cardinality as R.
Same cardinality as R?
Yeah. Because in fact, these two sets have the same cardinality. And it's pretty easy to convince yourself of that if you just think about reciprocals. Taking the reciprocal will blow this up into the interval from 1 all the way out to infinity. Every real number in between. So a reciprocal function gets us most of positive reals, at least from 1 on up, and then we've just got this little interval left. And there's theorems we can use to piece these together. What about all real numbers and positive real numbers?
That's what I'm saying.
Can you find a mapping?
We can find
been sleeping at 5 this morning, but I was awake doing stuff like this. So here's positive real numbers, here's all real numbers. So we can take this interval from 0 to 1 and map it down to here. And then we can take this next interval and map that here. And take this third interval and map it here. And take this fourth interval and map it here. And so on.
By alternating that, you'd never run out. You'd never run out, so you'd be able to.
But you never run out, so every number here will eventually be mapped from one of these intervals, and every interval here will map to somewhere on here.
And twice as many and a half times.
I know.
But the top,
It's annoying.
The positives go forever, so it doesn't matter.
Yeah, there's twice as many, but we still find this one-to-one mapping. Just like with integers, there's twice as many integers here as there are here, but we can still find a one-to-one correspondence.
We can also,
That's why cardinality is not the number of integers, it's this measure of size that works with infinity. And I don't have a good concept that I can put into words to describe what cardinality is. I don't know if it exists.
we can also reserve all negative ones, like for even positives, and all non-zero ones to odd ones.
Right, that would work. And again, we don't always need to find this correspondence to say two things are equal. We have the Russell-Bernstein paradox, or theorem, Bernstein-Schroeder, that says if one's greater than or equal to the other, and the other is greater than or equal to the first, then they're equal. And we'll punt to that sometimes. So the reals have a bigger cardinality than the integers. That's one answer for this question. And positive reals have greater cardinality than the integers. And anything that has the same cardinality as the reals will have the same cardinality. Will have a greater cardinality than aleph naught, cardinality of the integers. So intervals have the same cardinality as the reals. Complex numbers, that's just a pair of real numbers. So that's got cardinality certainly bigger than the integers. The interval from e to pi has the same cardinality as the reals. So there's lots of examples of sets we can construct. Once we know that the reals have a bigger cardinality, we can go crazy and just start cranking out different ones. I'm gonna put them on buttons and hand them out to strangers on the subway.
So cardinality of C and R is equal, right?
I believe so. I'm not going to swear to it off the top of my head, but I'm pretty sure. I think you have to get to the power set of R to get a bigger cardinality.
Oh,
Set of all subsets.
bigger than R?
Yeah.
I think that would be the third one I grabbed, which is really.
Oh, cool. Yeah, there is a theorem that the power set of a set has bigger cardinality than the set. And so the power set of the reals should have bigger cardinality than the reals. But what's unknown is, does there anything in between the integers, reals, power set of reals, and so on.
So the power set of integers bigger than the integers and smaller.
Power set of the integers, I believe, turns out to be the reals. But they still don't know if there's something between the reals and the integers. That's continual hypothesis.
What could be bigger than R?
The set of all subsets of R.
Okay.
Yeah.
Yeah.
So the set whose elements consist of any collection, including an infinite number of elements of R, that's bigger.
R to the R.
Maybe.
Because we can find solution for R to the R to 3, R powered by 4, but just like imagine R to the R.
Yeah, I'm not sure what R to the R would mean.
Subs of R.
Because if R is not an integer,
Infinite subs of
like when we do a set to a power, we usually mean Cartesian product that many times. But if that power is a non-integer, we need to extend that definition somehow. But it feels kind of like an R to the R.
It's like a chart that we have our columns and our rows.
Mm-hmm.
Then we would run out of R.
Yeah, something like that.
And it's going to be bigger than R.
Something like that, but R cross R I think is still R. You can double check this. That's certainly the same as complex numbers, because it's just pairs of reals. So cardinality won't be like a recurring theme in this course. It kind of is a topic on its own, but this notion of infinities is an important one to keep in mind, because when we write sequences, and we write a recurrence relation which says a(n) is equal to something, n is an integer, and n can get arbitrarily large. It can't be equal to infinity because infinity is not an integer. But this sequence can have an infinite number of terms. But if it's a sequence, it's got an order, we can count it. That infinite number of terms has cardinality aleph naught. And most of what we do in this course, our infinite sets, are going to have that same cardinality. And that's going to be important because that's going to let us do things like mathematical induction. And if we had a sequence where the number of terms in this sequence was the same as the size of the real numbers, we probably would not be able to write a recurrence relation in all cases. Because we can't define, well, I don't know if I can explain exactly why we can't, but think about it. So we're going to be concerned with infinities in here, but mostly they're going to be the infinities of the integers, aleph naught. But it's good to know there's bigger ones out there too. Other questions?
So for the index of a set, it starts with 0 or 1.
I don't think there's a defined standard.
Okay, so when we
So for a sequence, I think I started them from 1 the other day, and I started them from 0 today for some reason. But it's just an index. And if I wanted it to start from 1 and I started from 0, I can just use n plus 1 over on the other side instead of n. But I don't think there's a fixed convention for that. I don't have one. So do what makes life easy.
So, question number 4, is it true or it's,
That is true. That's distribution of unions over intersections. And you should be able to prove that with, I think we might have proved this in class actually. I think that was the example that I used in Berkeley. So yeah, if you just make the 8 rows of the truth table, you should
Somehow I
find.
found out
Yeah.
wrong.
Okay. Maybe the universe doesn't make sense. I just didn't know it. Anything else? All right, so back to propositional logic. So we talked about propositions, declarative statements that have a true or false value, deriving propositions from other propositions. We talked about conditional statements, which is another kind of proposition. We talked about variations on a conditional statement, contrapositive, inverse, converse. Some of those are equivalent to the original statement, some are not. So we can start to develop a whole calculating system around propositions, and it's going to look a lot like Engineering 250. Oh boy. So, a proposition and something that's true is going to be equivalent to the proposition. So if this is just some proposition and this is just a true proposition, just truth, and we take the conjunction of those, the and of those, that's equivalent to the original proposition. And if we do the or with a false, that's also the original proposition. That's the identity. Equivalent, thank you. If we do it the opposite way, if we do P and false, we get false. If we do P or true, that's equivalent to true. This is called domination. The false or true value dominates the proposition and becomes the value of the expression. If we take a proposition and we conjunct it or disjunct it with itself, I don't know if those are verbs, we get the original proposition back. That's called idempotence. We saw a double negation, I think, already. And we talked about commutivity. P and Q is the same as Q and P. Associativity, we can move the parentheses around. We talked about De Morgan's, and De Morgan's works for propositions as well. So the negation of conjunction is a disjunction of the negations and vice versa.
So I remember seeing this in Wolfram Alpha, whenever you did a and or logic tables.
Mm-hmm.
Is that just because they're the same, or?
Yeah, it's all basically the same. This is the same as doing this with Boolean values, and it turns out to be the same as doing what we were doing in sets with unions, intersections, and complements.
Why is there so many different notations for the same thing?
You wonder, huh?
Yeah, I was wondering that as well. Like, what's the point of creating all of these different notations to say the same thing in different like universes?
It's a good question. It would be nice to have sort of an uber subject that encompassed like 250 and set theory and Boolean logic and binary operations, and then all this would just be one thing. I don't know what the answer is to that.
They were developed at different times in different places.
They were developed at different times in different places, but why haven't they been integrated into a single?
You would think someone would have done that by now.
Yeah.
Maybe they are going to.
Maybe they're going to, and I think it's probably been attempted or is being attempted, but.
Like in basketball.
And you can quickly find yourself dabbling in things like category theory, which is like an abstraction of abstract mathematics. And people were going crazy over category theory back in the 30s, I think. And it's pretty horrifying when you jump into it, because it doesn't sound like you're talking about anything. It's so abstract. But it applies to so many different things. And a lot of areas of mathematics you can view from a category perspective. And the theorems of category theory map to the theorems in these particular disciplines, topology or algebra and so on. But it becomes really kind of mind-boggling quickly. And that may be what happens if we try to do that here, but I think it would be a cool program to pursue. See if you can start finding some sort of superset of these subjects.
I think one reason why they haven't not combined, like, put all documentation to be the same, is probably the same reason why we get a conversion metric. It's just, once you make that conversion, averaging has to change.
That's true.
You have to now have that conversion room, you have to have conversions for every inch to be a centimeter.
Right.
And
inertia is pretty powerful. And I still can't write j for the square root of -1, even though that's what we do in engineering classes, because I means current, and I still write I. So if I can't do that, it's probably unfair to expect me to be able to. But it's an interesting question, I think. So yeah, so these look familiar. You put up two more. So P or P and Q is the same as P and P or Q, which turns out to be just the same as P. And you might have to think about that one a little bit, but if P is false, this is going to be false, this is going to be false. If P is true, this is going to be true just because P is true. Q is irrelevant. And same thing over here. If P is true, this will be true also. If P is false, the whole thing will be false because this is false. And this is absorption. And then there's negation. P and not P is false. So we can use these to do things like the following. Maybe I can do this in 4 minutes. Got a feeling we're going to continue this tomorrow. So we want to show that two statements are equivalent. So the negation of P ORed with the negation of P ANDed with Q is equivalent to negation P and negation Q. Now we want to prove that these are equivalent. All right, this is what we're trying to show, which means we don't know if this is true or not. If I start from here and I apply some change over here and apply the same change over here, can I say that these two are equivalent to each other? No. Because I don't know that this is equivalent to this. I'm trying to show that. So here's what I'll see. Somebody will say negation of P, or not P and Q is equivalent to the negation of negation P and negation Q. And you've just made a logical error. We don't know that this is true unless we know this is true, and this is what we're trying to show. But it's tempting to say, oh yeah, this is algebra, we'll just do the same thing to both sides. And you come down and you get to some statement that's clearly true and say, therefore, this must be true. But you started with something that you have no way of knowing if it's true or false. So here's a really oversimplified example. Prove 1 is equal to 2. So I'm going to say 1 plus the integral from 0 to infinity of e to the x dx equals 2 plus the integral from 0 to infinity of e to the x dx. And I'm going to do some other things that fill my page up with calculations. And I'm going to multiply both sides by 0. And I'm going to get 0 equals 0, and that's true. Therefore, 1 equals 2. And I know you're not going to do that. But you can end up doing the same thing inadvertently by starting from here and doing things to both sides. Okay, so don't fall into that trap, and I'll nail you on it again and again until you recognize it. And eventually you'll recognize when you start falling into that pattern. So don't do this. If you want to show that these are equivalent, the only thing that you can do is write down one of these sides. And show that that's equivalent to something that you know it's equivalent to. For example, I can use De Morgan's theorem and say the negation of something ORed with something is the negation of the first, ANDed with the negation of the second. And I can say that's De Morgan's theorem. That's part of a valid proof. And so I can continue using these facts of equivalence and keep changing this into something until eventually I show this is equivalent to not P and not Q. And because I started with this and showed that it was equivalent to each of these things, now I can say this is equivalent to this.
So would the next step be using the Morgan's theorem again on the or the negation
Yeah, that sounds like a good step. So you can try this at home. We'll work through this tomorrow. We'll start from here and see how to apply these and actually change this into this exact form, and then we can say this is equivalent to this. But the more important part for now is don't start doing things to both sides unless you know this is true. And if you're trying to prove that, you don't know it's true yet. And we'll talk about that again and again. All right, we're out of time. I'll see you next time.
Mr. Macias, are you sure there will be a quiz on Friday?
There will be a quiz on Friday.
Okay.
Quiz on the stuff that was on the homework, so the first week stuff, not the second week stuff.
Okay.